Hello everyone, welcome to another video on group theory. Now I know this is another math video, but in my next video I'll be going over another video on quantum field theory. But for now, let's do group theory once more. So, in our last video on group theory, we talked about what group isomorphisms were. Now to recap, a group isomorphism is just a bijective function f, where f of a operated with b was just f of a wedge f of b, where for all a and b are members of G, and for all f of a, f of b are members of some group H. That's what a group isomorphism is. If this definition is confusing to you guys, then watch my last video. I cover it in full detail and motivated as well. So that's what a group isomorphism is. In this video, we're going to give examples of how group isomorphisms actually capture relabeling of groups and how the structure of groups transfer to another. So group isomorphisms are so powerful because if you prove something about one group, it's going to directly apply to another group that's isomorphic to it. So you don't have to go about proving many things. When you can just prove one thing, and it automatically transfers to others by default. So, first of all, let's actually prove that groups of order 3 are isomorphic. So a group of order 3 will consist of 3 elements: some element A, some inverse element, let's call it inverse element B, and then the identity element. You can check yourself that this is the general form of a group of order 3. It has to contain the inverse and the identity element, and then some other elements A. So what are the possible combinations? What are the possible operations for this group? That's an operation. I have A, B, E, and A, B, E. So A operated with A is going to be something. We don't know that yet. A operated with B is going to be E. A operated with E is going to be A. By the way, this is the identity element. This is the inverse element. B operated with A, that's going to be E. This is going to be E. This is going to be B. Here we have A. Here we have B. Here we have E. So if any of this was confusing, I recommend watching my first video on group theory. I talk about what a group is, and you'll learn what an identity and inverse is. So A operated A will have to be something, but what can that be? Well, there are 3 options here. We can say that A operated A. We can define that as A. We can define that as B. We can define A operated with A as B. We can define A operated with A as E. Those are our 3 options, since the group operation has to be closed. It has to give us some element that's in this group. And these are our 3 contenders. So which one is correct? Well, we can't say A operated with A is A, because that would imply that A is the identity element, since A operated with the identity gives A. So it can't be that, since A is defined to be separate from the identity element. A operated A also can't be B Actually, it can be B. A operative A can't be E for similar reasons, since A operative A being E would imply that A is the inverse element, and it's not that by definition. So our last option is A operative A can be B, and this doesn't violate any rules of group theory. So A operative with A has to be B for the group of order 3 to be a group, right? So A operated A ought to be the inverse element. So this is the only possible Cayley table for a group of order 3. And this automatically implies that all groups of order 3 are isomorphic, right? Since this was a general group that we've constructed, and we found that there's only one possible Cayley table. A operative A ought to be the inverse, right? And then the rest is just like vendu. Like everything just falls from the rest. So all groups of order 3 are isomorphic, since, well, there's only one possible Cayley table. So if I have like some other like group of order 3, let's say it's like triangle, square, and heart or something, we can just relabel each element from this group to the other group, since they all have the same structure, right? Since like how things operate will like yield similar values because there's only one possible KD table. So yeah, that's why all groups of order 3 are isomorphic. Next, let's talk about, well, let's prove that the trivial group, all trivial groups are isomorphic as well. So what is a trivial group? What is a trivial group? Well, the trivial group is just a group consisting of only one element. Now, what can that one element be? Well, obviously, it would have to be the identity, which is trivial. That's what it's called, the trivial group. The trivial groups are groups consisting of only one element. They are of order 1. And that element, the only possible element is the identity, right? Since the identity operated with the identity would just be itself, so the identity is also the inverse of itself, and operations involving the identity and solely the identity will also be closed, since the identity operated with the identity operated with the identity, and so on will be the identity, since the identity is like, will yield the identity by definition, and that's the only thing in this set. So the groups of order 1 can only contain the identity element. And this will imply that all groups of order 1 are isomorphic to each other, since all of these groups consist of only one element, the identity, and the identity has the exact same properties, right? So they have the exact same structure, so they are isomorphic to each other. I can have some other group, let's call this group F, that consists of, like, say, some element gamma, and I can just relabel E to gamma, and I'm done, right? So I can relabel E to gamma, and the properties are the same. The operations work in the same way, since gamma is an identity element, and so is E. So all trivial groups of order 1, are isomorphic to each other. So what's next on our list? Let's prove that if one group is abelian and is isomorphic to another group, that other group is also abelian. Sorry about that. So let's prove that if G, some group G is abelian, and G and H are isomorphic groups, then H is also abelian. So this proof is pretty straightforward, actually. First of all, what is abelian? Well, abelian just means that A operated with B equals B operated with A for all A and B's in some element G. Basically, elements commute under the group operation. Second, what do we do now? Well, notice that F of A operated with B is going to be F of B operated with A. By the way, our isomorphism F is mapping elements of G onto H. Just note that. So F of A operated with B will be F of B operated with A, since these guys are equal, so the function of both will also be equal. Since it's an injective function and also surjective. So yes, this is a property of, well, bijectivity. Third, F of A wedge F of B will be F of B wedge F of A, and that's just the definition for an isomorphism, right? F of two elements being operated together will be F of A wedge F of B. For all F of A and F of B, that's an element of H. Therefore, H is abelian too, right? H is also abelian, since we've just proved that the elements of H will also commute under the group operation for H. So that's how we prove that groups are isomorphic, and one is abelian, and the other must also be abelian, right? And this isn't any surprise to us, since remember, group isomorphisms, like, it captures the structure of groups. If one group is abelian Well, and it's isomorphic to another group. That other group has to be abelian since they have the same structure, since they're really just a relabeling of elements. So of course they'd have to be abelian as well. Lastly, let's prove that if F is an isomorphism and it's mapping G onto H, and G is cyclic, that implies that H is also cyclic. First off, what does cyclic even mean? Well, a cyclic group, it's just a group, it's defined as a group where one element generates the entire group, or where at least one element actually generates the entire group. So what does it mean to generate an entire group? Well, a generator of a group is defined as, well, a group consisting of one element repeatedly operated with itself and inverse. So what does that mean? So let's actually take this mumbo jumbo and make real sense out of it. So let's say I have some group G. G consists of A, B, C, D, and E. The generator of A is just defined as A operative A, operative A, operative A, and so on. And A operative with the inverse of A operative with the inverse of A, operative with the inverse of A again, and so on. That's what it means. That's what the generator of some group element means. You just take the group, you take the element, and you just form a set of the elements operated with itself over and over again, and operate by its inverse over and over and over again. That group that you get, that's called the generator of some element. And the group is also called, another name for it is a cyclic subgroup. And this is the generator of A. Now, if it turns out that the generator of A, or the cyclic subgroup, actually generates the entire group G that A is an element of, that group G is called a cyclic group. So let's give an example of a cyclic group. Let's get a new page. Alright. So the integers mod 3 is an example of a cyclic group. Just a reminder, the integers mod 3 consists of 0, 1, and 2. So the integers mod 3 consists of 0, 1, 2, and it's a group under the modular addition. So how is this a cyclic group? Well, let's take the generator of each element of the group to find out. So what's the generator of 0? Well, the generator of 0 is going to be 0, 0 plus 0, 0 plus 0 plus 0, and so on. And 0 minus 0, 0 minus 0 minus 0, and so on. Which, of course, is just going to consist of zeros all the way to like infinite order. So this, of course, does not generate the entire group, since the entire group is not just zeros, it's 0, 1, and 2. So this is a cyclic subgroup, but the entire group Z mod 3 is not a cyclic, well, it's not generated by 0, but it might be generated by 1. Let's see. Well, the generative 1 is going to be 1, and then 1 plus 1, 1 plus 1 plus 1, and so on. So it's also going to be 1 minus 1, 1 minus 1 minus 1, 1 minus 1 minus 1 minus 1, and so on, okay? Where minus 1 is going to be the inverse element of 1. And the generator of 2 is going to be 2. Like, you guys get the whole point, right? I don't have to, I can just speed through this, and so on. So, what is the generator of 1? So let's actually evaluate this. So 1, so it's 1. What's 1 plus 1? Well, 1 plus 1 is 2. What's 2 plus 1? 2 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 0, and so on. The inverse is the same thing. 1 minus 1 would be like technically the inverse is for 1, the inverse will be will be 1 plus. Wait, let me think about this. Yeah, the inverse for 1 will actually be 2. Since 2 gives it to, brings it to the identity element, and then that being 0, and then the identity element is of course going to be 0. So the generator of 1 is just 1, 2, 0, 1, 2, 0, and so on, which does generate the entire group, since the entire group consists of the exact same elements that the generator of 1 consists of. So this indeed is a cyclic group, since it's generated by at least one element, that being 1. Well, just for funsies, let's check if 2 generates the entire group. Well, we start with 2. What's 2 plus 2? 2 plus 2 is, so we go 1, 2, that's 1. 2 plus 2 is 1. 1 plus 2 is 0. 0 plus 2 is 2. And so on. Just repeat over and over and over again. And this is the elements of the generator of 2 are the same elements in the interest mod 3. So 2 generates the entire group. This is a cyclic subgroup. Like, all of these are cyclic subgroups by definition, but the entire group, the interest mod 3, is a cyclic group, since one of its elements, since one of its cyclic subgroups is equal to the entire group. So that's why the interest mod 3 is a cyclic group. So now we know what cyclic groups are. Let's actually prove that if one group is cyclic, blah blah blah, other group has to be cyclic as well. Blah 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 is isomorphic to another group. So let's prove that. Okay, first of all, we note that G is just A operated with A operated with A, and so on, and then A operated with the inverse of A, operated with the inverse of A, operated with the inverse of A, and so on. Also, I just want to note something. I wrote a -1 here for the inverse of 1. That's not actually correct. That was my bad. The inverse of 1 here is -1. So -1 is in the group. The inverse of 1 here is actually going to be 2. By -1, I just mean like the inverse of 1. I don't mean like the actual negative 1. Just by the way. Just so I want to make my notation get clearer. So this is going to be the group G, right? Since G is cyclic by definition. So H is going to consist of F of A operated with A, F of A operated with A operated with A, and so on. F of A operated with the inverse of A, and so on, right? Since H is isomorphic to G, our function acts on G, outputs H. So H is going to be F of A wedge F of A, right? Since it's an isomorphism, F of A operated with A will just be F of A wedge F of A. And then F of A wedge F of A wedge F of A, F of A wedge F of the inverse of A, and so on. And H is exactly cyclic, right? Since there is one element of H, that being f of A, that will generate the entire group of H, right? You just operate f of A by itself over and over and over again, and by the inverse of it over and over again, and we get the group H. Therefore, H is cyclic. That's our proof. So I really hope that this video pretty much like nailed into your head that isomorphic groups have the same basic structure. I went through these proofs to demonstrate that it is indeed the case that isomorphic groups have the same underlying structure. One is cyclic, the other is cyclic. One is abelian, the other is abelian. One is symmetric, the other is symmetric, and yada 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 and so on. So yeah, that is the fourth video on group theory. Next video I'll be doing quantum field theory. And yeah, that's pretty much it. Hope you guys have a great day. If you guys enjoyed this video, consider sharing it. And yeah, have an amazing day. Bye.